Hello, am I audible?
Yes,
Hello.
ma'am.
Okay. So, good afternoon all. Today we are going to start unit number 7 and that is group. Okay. So, today we are going to start with unit number 7 and that is groups. So, first of all, we are going to see what is definition for groups. Okay. So, in the last chapter we have seen what is the definition for semi-group, what is monoid. We can say group is a next version of this algebraic system that will contain all properties of monoid, but in addition to these properties, this group is containing one more property and that additional property is called as inverse property. Okay. So can anybody tell me what are the properties of semi-group?
Closure and associative.
Yes, closure and associativity. And for monoid,
Closure,
Closure
associative,
associative
and
identity.
identity.
yes, closure, associativity, and identity. So here this group is containing one more property in addition to monoid, and that property is a inverse property. So we can say that group must satisfy first closure, second one associativity, third one identity, and last one inverse property. So all these property, if that algebraic system satisfies, then that is called as groups. So here definition is given. A group G star is an algebraic system in which the binary operation star on G satisfies three conditions. Here they have given three conditions, but we can add closure property. That is first one as a closure property. So that is also necessary. So first one is for closure. So we can define closure as for all x and y belongs to G, x star y that is equals to x star y and that should belongs to group G. Means what? Once you perform that star operation on any two elements of group G, whatever result we will get, that is x star y, that should belong to G. That is first property. That is a closure property. Second property is for associativity. So here we are going to consider any three elements. Suppose these three elements are x, y, z. So for all x, y, z belongs to G, x star in bracket y star z is equals to in bracket x star y star z. So this property is called as a associativity. And next property is for an identity element. So we have seen this property earlier. Just a minute. So this third property is for an identity element. If there exists element E that belongs to G such that for any x belongs to G, x star E is equals to E star x is equals to x. Means what? Here E is an identity element. So if you perform any operation with any element and identity element, you will get that element only. This is the identity property. And last one, which is new for this group, that is inverse property. So for any element x that belongs to G, there exists an element denoted by x inverse. So this is the inverse. So if that x is element, then inverse of that will be denoted like x inverse. So x inverse belongs to G such that x inverse into x or x into x inverse, that is equals to E. Means what? If you perform that star operation on any element x and its inverse, you will get identity element E. So all these four properties must be satisfied by group. Then only that algebraic system is called as group. So these are the properties of group. So have we understood these four properties? Hello? Have we understood the properties of groups? Hello?
Yes, ma'am. Here one statement is given. The identity element of a group is unique and it's called as identity of that group. So here each and every group will be having only one identity element. Okay. So the inverse of any element of G star must be unique, and again what we have seen here, that is fourth property of this group, that is inverse property. This one, there should be inverse of each and every element. So again this inverse of any element must be unique. So there are two different modes. First one, the identity element of group is unique, and second one, there should exist inverse for each and every element. Again that inverse should be unique. So here they have given a group cannot have a zero element because every element in a group is invertible. Like if you consider element 1, so what is the inverse for this element 1? Minus 1. This is the inverse. Likewise, if you consider 2, then inverse for 2 is minus 2. So this is the meaning of this statement, as the group cannot have zero element. त्या group मध्ये आपण zero include करू शकत नाही, because we can't write inverse for this element zero. आपण zero चा inverse minus zero असं लिहू शकत नाही. That's why the group must not contain element zero. Rest of all elements we can include, like 1, 2, 3, 4, because inverse for all these elements are exist. Next one, a group cannot have any element which is idempotent except the identity element. If A belongs to G is idempotent, then. So what is meaning of idempotent property? So here they have written A star A is equals to A. So this is a idempotent property. So a group cannot have any element which is idempotent except identity element. So only identity element can have idempotent property. This is meaning of this statement. So again, we can get identity element E for any element A as A into A inverse. So again, we can replace this A by its idempotent property as A star A. So A inverse star A star A. Again, if you change this bracket, A inverse star A. So what is meaning of this? If you take star operation between a element and its inverse, then you will get identity element that we have seen here in the inverse property. So here that element is x, so x star x inverse, that is equals to E.
Likewise, A star A inverse, that is equals to E, and that we have written here. So again, E into A. That is E star A.
Hello, ma'am.
Now, next point is the permutation. So first of all, we will see what is the definition for permutation. Any one-to-one
Hello, ma'am.
mapping. Hello. Yes.
Last
Hello.
point repeat once again, ma'am.
Okay. This one for idempotent.
Yes, ma'am.
Okay. So what is meaning of this statement? Only idempotent element, that is, sorry, only identity element can be idempotent. So what is meaning of this statement? So idempotent property means what? A star A is equals to A. Means what? If you perform that any operation on element A, it will give A only. This is a idempotent property. Now, here we have seen how we can find out identity element E. So, if you consider that element as A, so we will get identity element E as A into A inverse. Okay. So, likewise, we have seen this property for inverse. So, X into X inverse is equals to E. Now, just we have replaced here X by A. So, A into A inverse, that is equals to E, and E is a identity element. Again, here we have written A is equals to A star A because this is idempotent property. So again, we can replace this first A by A star A. So now this statement becomes A inverse star A star A. Okay. Now here we can change this bracket as, because this is multiplication operation. So A inverse star A, this is one bracket star A. So again, what is meaning of A inverse star A? It is an identity element, that is E. So again, E star A, that is equals to A. So here only identity element can have idempotent property. We can prove. So this is just statement I have told you for your information. Now, yes, have you understood now?
Yes,
Just keep,
ma'am.
yeah, just keep in mind that only identity element can have idempotent property. Now next one is permutation. So definition for permutation, any one-to-one mapping of a set S onto S is called as permutation of S. So I think you have seen these concepts, permutation and combination in maths. Okay. So again, same concept we have to apply here. So definition is like one-to-one mapping of any set on itself is called as permutation. So there is one formula how to find number of permutations, and that is n factorial. Now suppose your set S is containing two elements, then number of permutations are 2 into 1 factorial, that is 2. Likewise, if your set S is containing 3 elements, then number of possible permutations are 3 into 2 into 1 factorial, that is equals to 6. So likewise, we can find out number of permutations. Afterwards, we have to solve many examples based on permutations. Just now, you should remember the formula for number of permutations, and that is n factorial. Next definition is for order. So the order of any group G star denoted by this line G. So what is meaning of this? This is an order of group G. So meaning of this order is number of elements of G. Now suppose your group G is containing 2 elements, then order for that group is 2. Now if your group G is containing 4 elements, then order of that group is 4. So order means what? The number of elements those are present in group G. And there is one condition, your G must be a finite. That is, group should be a finite group. So this is related to order of group. So have you understood what is meaning of order of group G?
Yes, ma'am.
Next definition, that is for abelian group. A group G star in which operation star is commutative is called as an abelian group. And so again, this abelian group, it is a group, and if that group is satisfying commutative property, then that group is called as abelian group. So can anybody tell me what is meaning of this commutative? Commutative means, suppose we have to apply this property for 2 elements A and B. So can you explain how we can justify commutative property for these 2 elements? Just we have seen what is meaning of idempotent. That is, for any element A, we can write A star A, that is equals to A. This is idempotent property. Likewise, we can define commutative property for any 2 elements as A star B is equals to B star A. So here they have given one example. Let I be a set of integers. Then the algebra I plus is an abelian group. Yes, because I is a set of integers, and here we have defined addition operation on these elements. Hello. Have you got idea about abelian group? Hello. So we will see this concept once again. Abelian group. What is definition for this abelian group? A group G star in which the operation star is commutative is called as abelian group. This what a group with an commutative property is called as an abelian group. So here they have given one example as if you consider set of integers I and if you define operation of addition on it, then it will form a abelian group because this plus operation is a commutative operation. So if you consider any two elements from this set of integers like 2 and 3, then 2 plus 3 that is equals to 3 plus 2. So it satisfies a commutative property. That's why this group is an abelian group. Have we understood what is meaning of an
Yes,
abelian
ma'am.
group? Okay. Okay. So here they have defined one set. That set is containing four elements as F0, F1, F2 and F3. So these are the functions, four functions under the operation of composition, and this is an abelian group of order 4. So can anybody tell me why order of this group is 4 only? We have seen what is definition for order of group.
Because the element number of element is 4.
Yes, because number of elements here in this set that is 4. That's why order is 4. Now they have defined this composition operation. How? First one F0 composition F0. So here we have to perform addition of indices modulo divided by 4. Why modulo divided by 4? Because this set is containing 4 elements. So if you consider F0 composition F0, here indices are 0 plus 0, that is 0. Again 0 mod 4, you will get 0 only. Again F0 composition F1, so 0 plus 1, 1. 1 mod 4, again it is 1. F0 composition F2, then 0 plus 2, 2. So 2 module divide by 4, again it is 2. So F0 composition F3, that is 0 plus 3, again it is 3. 3 module divide by 4, it is 3. That's why this composition is F3. So likewise, we can form this composition table. Now consider this composition F1 composition F3. So here indices are 1 and 3. So again 1 plus 3 it is 4. 4 module divided by 4 it is 0. That's why answer for this composition F1 composition F3 it is F0. So likewise we can form a composition table. Have you understood this problem? I think we have seen this kind of problems in function chapter.
Yes, ma'am.
Okay. Next question. Let G is equals to set of four elements, that is alpha, beta, gamma and delta. So here operation star is defined on group G, which is given by this table. Then here you have to tell what is an identity element for this group. or for this composition table. And again, we have to find what is an identity element here. We have seen this concept many times, how to recognize an identity element. Hmm. So which one is the identity element here? Alpha, beta, gamma, delta. Which one?
Alpha.
Alpha is correct because alpha star alpha, it is alpha. Alpha star beta, it is beta. Alpha star gamma, it is gamma. Alpha star delta, it is delta. Means what? If you apply this alpha on any element, you will get that element only. That's why alpha is an identity element here. Now, next one, we have to find inverse of each and every element like beta, gamma and delta. So, first I will tell you how to find inverse for beta. Okay. So now for this element beta, we have to check where we have written an identity element. So in this row, that is row for beta, we have written an identity element alpha here. And this alpha is given by that element beta. Okay. That's why inverse of beta is beta. So here in the inverse property, we have seen how to find inverse for any element. So here in this question, we know that element, we know an identity element, just we have to find its inverse. Okay, so the element which gives an identity element, that is called as inverse of that particular element. So here that element is beta. So for this beta, an identity element alpha is given by this element beta. That's why inverse for beta is beta. Understood how to find inverse? Hello? Okay. Next. Now suppose you want to find inverse for this gamma. So how to check which one is an inverse element? Again, we have to check which will give us an identity element alpha for this gamma. So gamma is here. So for this gamma, an identity element is given by this column and that column is for delta. That's why inverse element of this gamma is delta. Now you have to tell me what is the inverse for delta. Same procedure you have to apply. In that row, you have to search for which element has given us an identity element alpha.
Gamma.
Gamma.
Gamma is gamma, correct. Because for this delta, we have written an identity element alpha here and this element is given by gamma. That's why inverse for delta is gamma. So likewise, we can find inverse for each and every element from this group. Have you understood? So this is very important. Many times they have asked question for this inverse property for 4 marks. Okay. One composition table will be given to you and from that table you have to recognize an identity element and then you have to find inverse for each and every element. Okay. So now tell me what is an inverse for element alpha. अल्फा साठी इन्व्हर्स काय येणार आहे मग? Again, same procedure we have to apply here. For this composition table, an identity element is alpha. So for this alpha, which element has given an identity element alpha? Again, that element is alpha only. That's why inverse of alpha is alpha. So here they have given some properties of groups. Let G star be a group and A belongs to G. Define these following properties. A raised to 0, that is equals to an identity element E. A raised to n plus 1, this is equals to A raised to n star A. For any element n belongs to capital N. Second one, A raised to minus 1 raised to n, this is equals to A raised to minus n. And next one, A raised to m star A raised to k, this is equals to A raised to m plus k. Because base is same here, that's why we can take addition of its indices as m plus k. So I think all of these rules we have seen in mathematics. Same rules are here for groups also. So before some time we have seen what is definition for permutation. So mapping of any set with itself is called as permutation. So same permutation we have to apply here. One example is given and that set is consist of 3 elements as A, B, C. Then permutation P is given as mapping of set S onto S. So we have seen definition for permutation as mapping of set on itself is called as permutation. That's why permutation P is given as mapping of S to S, and it is bijective mapping. And that permutations are denoted here as P of A is equals to C, P of B is equals to A, and P of C is equals to B. Then we can represent this permutation as, because permutation P is applied here, so P is equals to, we can say A is mapped into C, that's why A is mapped into C, B is mapped into A, so B is mapped into A, and C is mapped into B. So this is the way in which we can represent any permutation. So meaning of these two ways is same, that is P of A is equals to C. So what is meaning of this one? If you apply permutation P on element A, it will give you C. So A is mapped into C. So likewise, we can represent any permutation. Again, this permutation can be, we can change the sequence of this ABC and CAB. That's why these permutations can be like, these three possibilities are given here. We can represent in any way. Now suppose if you consider this permutation P, where A is, now if you diagrammatically, we can is mapped into C. That's why there is an arrow from A to C. Now second one, B is mapped into A. That's why there should be arrow from B to A. And last one, C is mapped into B. So that is represented here. C is mapped into B. So direction of arrow is from C to B. So in this way we can represent any permutation. Have we understood what is permutation? How we can represent it?
Yes,
Hello.
ma'am.
Okay. Now here one example is given for permutation. Set S is given, which is consist of two elements A and B, and permutations P1 and P2 are given. P1 as AB, AB, P2 as AB, BA. Okay. Now from this we have to form a permutation table, and that permutation table we have to form with this operation. So we can say this is operation for permutation. Now we have to form permutation between P1 and P2. So rows are P1, P2 and columns are P1, P2. So how we have identified how many elements will be there in permutation table, because we have seen the formula for number of permutations is n factorial. Now here value of n is 2 because this set is containing 2 elements. So 2 factorial means what? It is consists of 2 elements. That's why your permutation table will contain 2 rows and 2 columns. Okay. Now suppose we want to find permutation between P1 and P1. So P1 permutation P2. Sorry, P1 permutation P1. So how to find this? I will show that example. So here this is the given permutation P1 and P2. Now we have to form this permutation table, that is first element of that permutation table is P1 permutation P1, and that can be solved as P1 permutation P1. So value for P1 is AB AB, again permutation P1. So again we have to take same value as AB AB. Now, in order to take permutation, this second and third element must be same. So 1, 2, 3, 4. So again, this second and third element must be same. Then only we can cancel it. Now check here. That element is AB. Again here, that third element is AB. So these two elements are same. That's why we can cancel it, and we will get AB AB as final result. Now check, this value is for this permutation P1. Yes, here that is P1. So we can write the value for P1 permutation P1 as P1. So this is the first value. Now we have to find the value for P1 permutation P2. Now check here. I have solved that here. P1 permutation P2. Now value for P1 is ABAB, that is given. Value for P2 ABBA. Now again check whether second and third element is same. Yes. Here second and third element is ABAB. That's why we can cancel it. So we will get ABBA. ABBA. Now check ABBA, that is given for permutation P2. So value for this P1 permutation P2, it is P2, and that we have written here in this composition table, that is P1 permutation P2, it is P2. Now first row is completed. Now check for permutations of P2. So first P2 permutation P1. So again we have to apply same procedure, P2 permutation P1. So value for P2 is AB, BA, and value for P1 is AB, AB. Now check whether second and third element is same. No, here it is BA and third element is AB. So now this AB we have to convert into BA. So how we can do? We can interchange the columns. So AB will be converted into BA. So BA, BA. We have interchanged columns in order to make this AB to BA. Now check here. Second and third element is same now. So we can cancel it. So after cancelling this, we will get AB, BA. And this AB value for the P1 it is P2. Now just one value is remaining, that is this last one, P2 permutation P2. So again same strategy we have to apply here, P2 permutation P2. Value for P2 is AB BA. Again value for P2 is AB BA. Again check whether second and third element is same. Here second element is BA and third element is AB. So again we have to convert this AB into BA. That's why we need to interchange the columns. So if you change this AB into BA, this AB BA becomes AB. So this BA BA will get cancelled. You will get AB AB. And this is the value for permutation P1. That's why we have written here in this table P2 permutation P2 is P1. So in this way we can form any permutation table, and based on this you will get question for 4 or 8 marks to form a permutation table. So have you understood? Hello?
Yes, ma'am.
Okay. Now in the next example, they have given one set and that is consist of 3 elements. Okay. So 3 elements means what? How many permutations will be there?
6.
6 permutations, because 3 factorial, 3 into 2 into 1 factorial, and that is equals to 6. So all those 6 permutations are given here as P1, P2, P3, P4, P5 and P6. Now from this we have to form a permutation table. But before that we can draw diagram for each and every permutation. Now consider permutation P1. Okay. So P1 is consist of 3 elements, 1, 2, 3. So all these 3 elements are represented here as 1, 2, 3. Now 1 is mapped into 1. So there is arrow from 1 to 1. Again 2 is mapped into 2 and 3 is mapped into 3. That's why there is arrow from 2 to 2 and 3 to 3. So this is the diagram to represent permutation P1. So likewise we can represent permutation P2 as 1, 2, 3, 2, 1, 3. Means what? 1 is mapped into 2, 2 is mapped into 1 and 3 is mapped into 3. So that is represented here. 1 is mapped into 1. Sorry, I think something is wrong here. Here they have given 1 is mapped into 2. So there should be arrow from 1 to 2. And 2 is mapped into 1. Again there should be arrow from 2 to 1. And then 3 is mapped into 3. So 3 is mapped into 3. So there is one correction in this permutation P2 where 1 is mapped into 2 and 2 is mapped into 1. P3 is given as 1 is mapped into 3, 2 is mapped into 2 and 3 is mapped into 1. So there should be arrow from 1 to 3, 2 to 2 and 3 to 1. So 1 to 3, 3 to 1 and 2 to 2. Again, for this P4, we can draw diagram where 1 is mapped into 1, 2 is mapped into 3 and 3 is mapped into 2. 1 is mapped into 1 means there should be arrow from 1 to 1. 2 is mapped into 3. So there should be arrow from 2 to 3 and 3 is mapped into 2. That's why arrow from 3 to 2. So likewise, we can draw diagrams for P5 and P6 as 1 is mapped into 2, 2 is mapped into 3 and 3 is mapped into 1. And for P6, there should be arrow from 1 to 3, 2 to 1 and 3 to 2. So likewise, we can represent any permutation diagrammatically. And after that, we have to form this permutation table. So here total 6 permutations are there. That's why in the permutation table, there will be 6 rows and 6 columns. So all these permutations we have to find, but this example is quite lengthy. Some of the permutations I have solved here. So likewise, you have to solve all these permutations and finally you will get this permutation table. So this example we will see next lecture. So first of all, tell me whatever concepts from groups we have covered today, have we understood? Yes.
Yes, ma'am.
Oh, good. So this next example based on permutation we will see next lecture. Just give me percentage. Roll number 1,
Yes, ma'am.
2,
Yes, ma'am.
3,
Yes, ma'am.
4, roll number 4, 5,
Present, ma'am.
6,
Present, ma'am.
7, roll number 7, 8,
Present, ma'am.
roll number 9,
Present, ma'am.
10,
Present, ma'am.
11,
Present, ma'am.
12,
Yes, ma'am.
13,
Present, ma'am.
14,
Yes, ma'am.
15,
Present, ma'am.
16,
Present, ma'am.
17,
Present, ma'am.
18,
Present, ma'am.
19,
Present, ma'am.
20, 21, 22,
Present, ma'am.
23,
Present, ma'am.
24,
Present, ma'am.
25, 26,
Yes, madam.
27,
Present, ma'am.
28,
Present, ma'am.
29,
Yes, ma'am.
30,
Present, ma'am.
31,
Yes, ma'am.
32,
Present, ma'am. Present,
33,
ma'am.
34,
Present,
35,
ma'am.
36,
Present, ma'am.
37,
Present.
38, 39,
Present, ma'am. Present, ma'am.
40, 41,
Yes,
42,
ma'am.
Present, ma'am.
43,
Present,
44,
ma'am.
45, 46,
Yes, ma'am.
40, okay, 47, 48,
Yes, madam.
49,
Yes, ma'am.
50,
Yes, ma'am.
51,
Present, ma'am.
52, 53, 54,
Yes, ma'am.
55, 56, 57,
Yes, ma'am.
58,
Yes, ma'am.
59, 60,
Yes, ma'am.
61,
Yes, ma'am.
62,
Present, ma'am.
63,
Present, ma'am.
64,
Present, ma'am.
65, 66,
Present, ma'am.
67, 68,
Yes, ma'am.
69, 70, roll number 4, 7, 21, 25, 34, 38, 41, 45, 47, 52, 53, 55, 56, 59, 69, and 70. So these are the option numbers.
Ma'am,
Yes.
38 present. Due to network problem, I left the meeting.
Roll number
38.
38.
Ma'am, 36 also present.
36.
Yes.
36 I have marked present only. Thank you. So today we will stop here.
Hello, ma'am.
Hello?
मॅम 59 प्रेझेंट होता.
Hmm?
ते नेटवर्क इश्यू मध्ये डिस्कनेक्ट झाला तो.
59.
बॅटरी पण नाही म्हणतोय. हां. आता मला मेसेज
Okay.
आला तो.
Hmm. Okay.
थँक्यू मॅम.
Hmm. Good? Okay.